we are going to do a really functional and really brief overview of how X-ray diffraction works. If you take a class, and I don't know how deep your class goes, but if you take a class, it is possible to study X-ray diffraction for weeks and weeks and weeks. And there is some really cool math, there's some really cool geometry, there's some really cool physics. Okay, well, so you're not going that deep, that's good. The problem that I see sometimes with those classes is unless you have a really clear view of what XRD does from the beginning of that class, it can be really easy to get lost in the calculations of it. And actually all of that conversation can make it a lot harder to run an XRD than it would be if you just understood the basics. So what I'm trying to do here is just talk about the basics of X-ray diffraction with the purpose of you understanding when I throw a sample into an XRD, what's happening, why am I doing this, what materials is this useful for, that kind of stuff. Super fun. So XRD is the 3-letter acronym for it. It stands for X-ray diffraction. Do you know the difference between diffraction and reflection?
Diffraction when it goes like this,
Mm-hmm.
and reflection like a mirror.
Yes, both of them are something bouncing off of a surface, but diffraction has a very specific angle in and angle out. So it's where the light is being bounced off the surface in a very regular way. Reflection can be any of those. Controlled is not the word I want to write. It's like reflection, but more predictable. It's super fun. All of the notifications all the time. And in this discussion, I'm going to be focusing specifically on something called Bragg-Brentano orientation. Have you heard those words before? This is more commonly referred to as powder XRD. Oops. So Bragg-Brentano orientation is assuming that we have randomly oriented grains, whether that's because it's a powder or because it's a metal with randomly oriented, grains. And homogeneity is important here. Scam call. It's fun. We weren't having enough fun with all the notifications in the background. Go away, potential spam. Stop calling me. Ha. So I'm going to be talking about this Bragg-Brentano orientation, basically meaning that we're talking about randomly oriented grains, as opposed to if we were running something that was crystalline, that was like a single crystal. Single crystal XRD is its own whole field of study. And it does have differences to what I'm going to talk about today. There are principles that stay the same between all of them because physics doesn't change. Physics is physics. But what I'm talking about is assuming this kind of random orientation. So this starts with something called a goniometer. which a goniometer is measuring the angle in a circle. So I've got this that I'm, drawing by hand, so please forgive my not circular circle here. But we've got a half circle. And a goniometer helps us know where on that circle we are positioned. So measuring the angle along this circle. And this circle is actually, you can think of it like a clock, where I've got like the center of the clock, and there are arms that stick out from either side of the center. And those arms hold things at the ends of them. In most instruments, actually, in most instruments we have on the left-hand side of this clock or this goniometer, we have a source of X-rays. So on the left-hand side, we've got the source of our X-rays. The X-rays come from a tungsten filament. We put some current and voltage through that filament. For our biggest XRD, it's 40 kilovolts. Oh, let's see. It's 45. I apologize. Not that makes the biggest difference, but we do 45 kV and 20 milliamps for our largest. For our smallest, we do 30 kV and 10 milliamps. So it totally just depends on the instrument you're using, what strength you're using. And that does have an effect on the final power of the X-rays, but I'm not going to talk about it. So your instrument is going to have recommended parameters is basically what I'm saying. And by putting that voltage and that current through, goodness, we get an electron that comes off of that tungsten. It smacks into a copper, what we call an anode. And that copper anode is going to put out an X-ray. So this right here is our source. If I were to zoom in on the inside of it. And what that means is I have X-rays shooting out of my source. And these shoot right toward the middle, or sort of this center axis, where I have my sample. And for a lot of this, I'm going to draw an X-ray as if it were a flat line. I'm not going to do the wiggles every single time. I do not have the dexterity to draw that many X-ray wiggles. And then the X-rays are going to bounce off the sample at different angles. So on the other side of the goniometer, I am going to place a detector. Really commonly, this is going to be a photo multiplier tube, which basically amplifies the signal to the point where we can identify when an X-ray hits the detector or not. Because a singular X-ray does not have all that much energy, and for a detector to be that sensitive would be very expensive. So typically we're going to have a photomultiplier tube. There are other types of detectors that can measure X-rays, and they all have different trade-offs on sensitivity and clarity and position indication and all of that. Through all of this, I am measuring the position of both the source and the detector, because the source has the ability to move up and down just like the hands of a clock, and the detector also has the ability to move up and down just like the hands of a clock. Any questions so far or discrepancies with what you've learned? Cool. Yeah. While we are running this, like I said, we're measuring our position, and the instrument reports the position as the value 2 theta. I really should just silence that so it doesn't keep happening, but here we are. So what we do is the instrument is going to continue the source line, the angle, whatever that angle is that the source is coming from. If that line were to continue through the sample, we then take from there up to the detector, and that is 2 theta. You also could say it as a sum of this angle and that angle. Yep. The trick here is that 2 theta is not always equal to 2 times this or 2 times this, even though we call the angle from kind of the horizontal to the detector, we call that theta. And sometimes 2 theta is not always equal to 2 times theta. In this kind of way we're orienting ourselves, it often is. Usually the detector and the source are at the same angle on each side, so theta is equal to half of 2 theta, but not always. Why? Because we, well, I guess my theory is I don't have exactly sound backing on this, so I apologize if I'm wrong. My assumption is that we first noticed this on specific materials where theta and 2 theta were equal to each other in the way you'd expect. That theta and half of 2 theta were the same as each other. That is sort of the simplest and most straightforward orientation of things. And my guess is that's how we did XRD for a really long time. And then my guess is that we expanded and we got more complicated and we figured out new things we could do with it. And we started decoupling these 2 angles to see how that affected the results that we got. But we kept the nomenclature of 2 theta and theta. When we are talking angles, we call the sample or the source angle omega. So that's the like curly W, that's a lowercase omega there. So that's fun and a little bit confusing sometimes. So it's important to recognize when we're talking about 2 times theta versus 2 theta as if 2 theta were its own independent variable. But theta plus omega equals 2 theta. That one is always true. Yeah? Confusing enough? All right, so something worth knowing is that our x-rays coming out of our source here are going to have, they're going to have a little bit of scatter. So there's the possibility that I'm going to have x-rays going kind of every which way. But if I need to know the angle that they're hitting the sample, then I need to have them coming out at a very nice, clean, straight line. So we have to refine source, oh boy, x-rays. We can do that with slits and masks.
What do you mean by that?
So a slit or a mask, it's two different words for effectively the same thing, but it is a physical barrier to to x-rays that are errant, x-rays that are off kind of the expected course. To draw it out, oops, that was way too thick a line. So let's say my source is putting out this kind of wide spray of x-rays. I can stick a physical barrier let's see how we're going to draw this. So I can stick a physical barrier in the path, and I'm going to attempt to erase all the lines to make it look like a three-dimensional structure here. And going slowly. Okay. So here's my three-dimensional structure here. Is I've got these like three lines. Goodness. I've got these three lines that are able to pass through in this like opening here in the middle. And then these three that got stopped by this just like literally physical barrier to chunk of metal that will absorb the x-rays. Do you want to take a moment to try to draw that? Sorry, I've turned this into sort of a three-dimensional art class here. Not my intention, but it is just a side effect of drawing physical systems.
So it just lowers the scattered X-ray, it doesn't really stops everything.
Yep, so it's gonna stop those like x-rays that would have come out at really wild angles off of my one expected angle. And then I could set another mask, so these are going to continue moving outward, right? These ones. I could set yet another mask in the pathway, down the line a little bit. And get an even better refining effect. So now by putting sort of a second mask in the way, I've refined out even more of these x-rays, and now I have this one x-ray that's just like passing straight through everything. So we can use a combination of slits and masks to refine in both directions. What I've drawn here is two-dimensional, where I'm refining in this direction. But if I was talking 3 dimensions, I could also do this like in and out of the screen refinement as well. Because I do have a full, like, I have some x-rays going into the screen and some x-rays coming out of the screen, and kind of going every which way. Yep. So I can put a range of these. Another refinement that often happens is a monochromator. Goodness. A monochromator, so mono meaning one, chrom meaning color, and ater being a suffix of doing. What this is going to do is this is going to make sure we have only one wavelength of light. Copper has 2 main X-rays that it puts out. Yeah. It has copper K alpha 1, that's what I've drawn there, and then K alpha 2. So when I hit that copper anode back up here, that copper anode with those electrons, I end up with 2 wavelengths, that come out. Copper K alpha 1 is the one that's more prominent and is 1.5406 angstroms for the wavelength. K alpha 2 is 1.5444. We are talking about a difference of thousandths of an angstrom. We use angstroms to measure the size of molecules. Like, angstroms are so small, and we are talking thousandths of an angstrom. So to us, we're like, yeah, 5406, 5444, like those are the same effectively. We will talk in a little bit about why those are not actually the same, but it comes down to physics. They are going to have slightly different interactions with the world around them because one is a little bit bigger than the other. Not by much, but a little bit. So a monochromator is this big, long thing that has the ability to bounce the X-rays back and forth. And it's got these mirrors at each of those points. Those are little mirrors. The black lines that I drew are just the mirrors bouncing it back and forth. And different wavelengths are going to have slightly different paths and are going to be reflected at maybe a slightly different angle. So if I were to use, I'm going to use this yellow color for the K alpha 2 just for a moment. So they come in together and it gets reflected just a little differently. And it gets reflected just a little differently. And by degrees, it's getting reflected differently enough. You see how, like, I deviate slightly here I deviate a little bit more here, and I deviate here until that X-ray is lost inside the monochromator, and we end up with just the orange coming through. This would be like using a prism also to separate wavelengths of light, where we're using to our advantage the difference in kind of the length of the wavelength. That was a silly way to put that, but. So monochromators can be one way to refine, make sure we have only one wavelength coming through. We could also, sort of a subset of this monochromator, is you could also use a nickel filter. Nickel absorbs a percentage of copper X-rays and can sometimes diminish the effect of K-alpha 2. It's not as good as a monochromator, but it can sort of like help. Okay. And then we actually can have all of the same stuff. I'm zoomed way out because I want to see the whole height. So all of that same stuff that can refine the source X-rays can also refine the what do we call it? We could call it like the sample beam, or the source and there's a word. Yeah. I'm gonna write beam before the detector. There's a name that I can't remember right now for the beam on the right hand side of the instrument. But we can have slits, we can have masks, we can have a monochromator, a bunch of other things. Oh, Solar slits, I forgot to mention. Well, that's unfortunate. We are going to select this beast and extend it down a little bit because there is one more thing that I neglected. No worries. A solar slit. This is easier to draw in 3 dimensions and also harder to draw in 3 dimensions. So a solar slit is this kind of big rectangular prism kind of shape. It's usually fairly long.
Why? There's so many ways.
And it's got these parallel, they're little like pieces of aluminum foil. So if you can imagine that we're making like, what's an example of this? I can't think of a good like real world example, but we take this line of foil here. It'll be easier I think if I do like a zoomed out version. So I have one piece of foil imagine like aluminum foil, tin foil, etc. that you'd have in your kitchen.
Mm-hmm.
It's really thin and this is really flat. And right next to it, perfectly parallel with it, I stick another piece of foil. This one's in front of the other one. I now have this sort of gap between them, right?
Right.
Looks like that, and I've got sort of this like, I got this gap between them. And if any X-rays are traveling parallel to this gap, it could go in between the foil and go all the way through and come out.
What does that mean? What does that mean?
What does that mean?
Yeah, that it was like a.
So it means that it was perfectly parallel. Let's say I have something that is traveling maybe in the screen. It's not perfectly parallel with this line. It's traveling in. It may enter this gap between them, but it's going to end up running into my back piece of foil. Looking from above, I have these pieces of foil. That's what these black lines are. I have my perfectly parallel X-ray that makes it through. And I have my not perfectly parallel X-ray that whacks one of the walls. And I can... I'm going to change colors on some of these to make it a little bit more obvious what I'm doing here. Goodness. I'm getting blue dots everywhere because this darn thing won't click out of the right mode. And then see if I can grab both of those at the same time without grabbing anything else. There we go. So here I've got sort of a side view. Here I've got a top down. But these are two pieces of the same thing. By making this super long, we're going to refine out anything that isn't parallel perfectly within that like 1 inch or 2 inches. Usually these are fairly long. Was that confusing enough?
Like how long?
How long what? Sorry?
How long?
2 inches.
Oh.
Let me see if I can shrink that a little bit because I did make that a little bit excessively large. Good. Solar slits. Coming back to where I had been previously, but all of these things can also refine the beam after the sample, but before the detector. So everything that has diffracted, we call that the diffracted beam. I feel like I was so close just a moment ago. Okay, let's do a really quick overview of like a crystallography or like a ceramics course or a metals course would go over some of this also. Have you heard of something called a unit cell? What is a unit cell? Just really like briefly.
It's just like a repeated croissant.
Exactly. We typically will draw atoms as corners, and I have some three-dimensional structure, and I can take this structure and I can stick it right next to itself, and I get this repeat unit. Or I can stick it below itself and I get this repeat unit. Messy, drawn unit cell. It is just a building block. For crystalline materials. Good. What is a definition for crystalline?
Unorganized units where
Yeah.
units where it's just organized.
Yeah. Long range organization.
Yep.
Among either that's the atoms or molecules. Do you know the antonym or the opposite of a crystalline? Non-crystalline is a good word. Amorphous is the other word, which basically means random orientation, no long range order. And we can have semi-crystalline, which means it's a little bit crystalline and a little bit randomized. And when there's a whole bunch of different types, here I have drawn a very simple cubic building block or unit cell, but there are all sorts of orientations. You can have rectangular, you can have it more shaped like a trapezoid, you can have it shaped like a hexagon, you can have the cube be smushed or like slid in one direction or another. I'm only going to draw cubes because I am drawing by hand and I do not have any additional skills. But if you Google unit cell types or unit cell configurations, there's these really nice computer drawn pictures of what a more complicated unit cell might look like. They're not all cubic. I'm just going to keep drawing cubic. When we are talking about a unit cell, do you know how we measure a unit cell? Totally fine. So we have the width, the depth, and the height. We call them A, B, and C. Yep, precisely. We also have angles. I think I have drawn those incorrectly. One there, and one is on the flat, so I think maybe it's that one. Anyway, I have three angles, and we call the angles alpha, beta, and gamma. Are you looking it up for me? You're so good to me, thank you. I know one of them's on the left side, I know one of them's on the top, and I think the other one is in a third dimension that I have not drawn here, because I think it's between the bottom of the kind of cube and the back of it. I think it's actually this. Oh, that is the same thing as what I drew already. Oops.
Just in the kitchen.
Thank you.
You're welcome.
Oh, that's clever, actually. They have it all organized on the same, yeah, around the same angle. So if I were to draw my,
I saw that, but I was like, I don't know if you want that.
I mean, I think that's a clever way to do it. So you have an angle between these two front. Have one there, and then I have the angle here. And I've got alpha, beta, and gamma, is what I call them.
Yeah.
Let's say I convert this into a two-dimensional thing. And I have a structure of atoms that looks like this. Something like this. So I've got large atoms and small atoms. This is actually exactly what sodium chloride looks like if I were to just take sort of a cross section. And the genius of technology is that I can just sort of copy and paste this, and behold, twice as many circles as I actually drew. Would you be able to identify my two-dimensional unit cell in this?
Just like this. Then like this.
It would go from same atom to same atom, like this. It could also go from small atom to small atom, so I could go something like this. And in sodium chloride, it is actually cubic, so I have done a bad job of drawing squares here. But the idea is it sort of starts, each corner is in something that repeats. So I could take this same thing and I could go to the next one and I'd find the exact same atom. And I could go again that same distance and I'd find the exact same atom. So that's my basic unit cell, which means if I were to draw a line, don't use red and green together, that's a bad choice. If I were to draw a line through these two, you'll notice that those lines are identical, right? They pass through first a big atom, then a small, then a big, then a small, and both of them start with a big in the same position. What is the distance between these two in terms of A and B and C?
A bit C.
Yeah, so that distance would be C. That looks like an E. It's not, I promise it's a C. Now, let's take another line. This one that was sideways. Could you, if you had to, use geometry to figure out that distance in terms of A or B or C?
Yeah.
Yeah, you could do it, right? What we do, instead of trying to identify every single one, we call all of them D. A D spacing is a space between two identical planes. Good? I did not. Nope. I was just readjusting myself. I am drawing in two dimensions, which means my planes, quote, look actually like lines. In three dimensions, a plane is more like a sheet of paper, right? Big flat thing. But the spacing between these two identicals we just call D. And you can see D1 and D2, my blue D and my purple D, those are two different distances. But we refer to them still as D, because I don't know why, that's just the rules. Okay. Let's redraw my crystal structure, my very imperfect structure here. Oh, interesting. I forgot I already had that. I still had that copied. Stop it. I can tell. Oops. I can tell when my OneNote notebook is becoming too big because it jumps all over the place. So we're gonna redraw my crystal structure here. Wow, the marvels of technology. So many fewer circles that I had to draw. So much longer because it's jumping me everywhere, but hey, whatever. And I am going to redraw this blue repeat line. That was really terribly drawn, but there you go. And I am going to add actually one more layer down. Get myself a third. Wow, I am not at all drawing straight. It's fine. Now I'm going to put this crystalline material into an XRD. And I'm going to have X-rays of some known wavelength coming in at some known angle. And from this point forward, I'm going to draw the X-ray as a line because my drawing skills. So some of the X-rays are going to bounce off that first plane. Some are going to travel through. They're going to bounce off the second plane. And some might even travel through and bounce off the third plane. So what I end up with is 3 parallel but different X-rays, because they've all bounced at different points in their kind of zigzag cycle. I'm not looking at your drawing, I'm looking at your face to make sure you're good.
Yeah.
No one's looking at your drawing. I'm publishing mine on the internet. I'm in the wrong field. That field currently is artistry, and we're doing our best.
Okay.
Those X-rays then are going to bounce out of the sample at some angle we call theta.
Is it all the same theta?
Yes, they're all going to bounce off at the same theta. And we're talking, angstroms of depth. We're not talking significant. I've zoomed way in. Effectively, all 3 of these are on top of each other. They're not separated by this big blank space that I've drawn. Effectively, they're all right together.
Well, they're really close.
Really, really close together. Yes. And what happens is sometimes, depending on this kind of incoming and outgoing angle, and depending on the wavelength here, and depending on how far they had to travel, which that's related to the spacing between these and, this incoming angle, right? I could use a little bit of geometry to figure out this angle based on this distance and that distance. Got a little geometry situation going on here where I can solve a right triangle. So depending on all of those things, I will sometimes get constructive interference between my three x-rays up here. Constructive interference is when highs and lows line up with each other. Again, I am only a person with a hand to draw. This is where the highs and the lows align. And they all add together to make a large signal. So what we sort of create is this. Really big X-ray out of three smaller X-rays that all lined up together. It's like in a stadium when you do the wave. It's one person standing up and sitting down, but surrounded by hundreds of people standing up and sitting down, you get this really large signal. Yeah? Other times we're going to get destructive interference. This is the opposite. Oh my heavens. This is where, well, we're gonna just start that line over. This is where my highs and lows are opposite of one another. There we go. So I've got sort of inverse signals, and they add together to cancel out. And we end up with this just like very like nothing signal. And early physics people noticed this phenomenon. They were like, hey, sometimes I'm getting like a lot of signal. Sometimes I'm getting like no signal. And someone with the last name of Bragg came up with an equation that they named Bragg's law. You're nodding your head because we talk about Bragg's law a lot. I want to make it clear, Bragg's law does not decide whether constructive or destructive interference happens. Bragg's law helps us predict. So it is not a dictator, more a fortune teller. But like a scientific fortune teller, they're never wrong. So Bragg's law is not going to like decide that there is constructive or destructive interference. It's a way for us to predict when there's going to be constructive or destructive interference. I'm confident you've got it in your notes from classes where you've learned it. Do you know it off the top of your head? It is n lambda equals 2d sine of theta. I'm going to clarify this just a little bit. It is n lambda equals 2d sine of 2 theta divided by 2. Which seems like a really stupid clarification, but going all the way back up to the top, I'm talking about this 2 theta. I am not talking about this theta. I'm realizing I wrote it here too. I am not talking about this theta. I am talking about omega plus theta. So it is 2 theta divided by 2 is the actual value we're using there. Do you know what n is?
In this case,
Generally.
number.
It's just a number, it's an integer. It's easiest if we set it to be 1, but it could be 2 or 3 or 4. It will never be 2.5. It will never be 3.5. It'll never be pi, just some boring old integer. Lambda, where do we get lambda? It's the wavelength, yep. Do you remember those values from earlier I gave you? K alpha 1 and K alpha 2? This is where those come into play.
Which one do you want?
It's normally K alpha 1, which is 1.5406. Yep. It is sometimes 1.5444 angstroms, that K alpha 2. D is the spacing between the like repeat planes. And then
Didn't we have like D1, D2?
yes, right now I am looking at one specific D. I chose this blue one here. We'll talk about that in just a second, the different D spacings. And then 2 theta is omega plus theta, or the source incoming angle plus the detector's position, or the outgoing angle of that X-ray. If the equal sign is true, we predict constructive interference. So if the equal sign here is true, so if some integer times our wavelength is equal to the D spacing we're looking at times 2 times the sine of 2 theta over 2, then we predict constructive interference. Equal signs are really tricky, especially when you're working with a sign value. Like a single decimal can change, suddenly they're not equal to one another. So if the equal is not true, which is most of the time, we predict destructive interference. Good? So Bragg's law, again, is not a dictator. It's not like telling the material to do constructive or destructive interference. We are observers in this situation, but we use it as a fortune teller, as a way of predicting, of knowing, should I see constructive or destructive interference? I think I want to talk about the graph next. I absolutely do. And then we'll call it for you and me. So we usually put our X-ray as a 2 theta on our x-axis, so that's that omega plus theta. And our y-axis is going to be something like counts or intensity. It's basically like how many X-rays did the detector receive. And constructive interference is going to be really high. So we're going to end up with jumps up. And then destructive interference is going to look like essentially nothing. So I'm going to have this essentially nothing at first. And then I can get constructive interference that might look something like this. And these bumps up, depending on how tall they are, is telling us something about how frequently we're getting X-rays bounced off that position. When I threw this sample into the XRD, I am able to measure my source angle, I can measure my outgoing angle, and I know my wavelength, right? I even wrote them down here. The one unknown when I stick my sample in is usually that D spacing. Yep. So to do some example calculations, super fun, and it does that. Let's say I have a peak at 15 degrees 2 theta. So I get a jump there. I can use Bragg's law to predict that means I have some D spacing that was causing that constructive interference. And I can put that all together. So 1, that's N, times lambda, 1.5406 angstroms. N lambda equals 2 times D times sine of 2 theta over 2, 15 over 2, right? And I can solve all of that. In this case, D is 5.9 angstroms. So I have some spacing between two things that are 5.9 angstroms apart. I could grab another one. Let's say I have a peak at 80 degrees 2 theta. 1 times 1.5406 equals 2D sine of 80 over 2. And I have D equals 1.2 angstroms. If I were to label those on my screen, actually that's probably more like here. So you'll notice that this down here is larger D, 5.9 angstroms. And you'll notice that the higher 2 theta was a smaller D spacing at 1.2 angstroms. So 2 theta and D are inverse of one another, but it's really easy to convert between these peaks that I'm getting from the instrument and what D spacings are present in my material. So let's talk then about why we care about some of the different values in this equation. So first of all, I've got N. Why do we care about N? So at the same D spacing, so let's say D equals 8.8 angstroms. I've just got this one spacing in my crystalline material. If N equals 1, then I expect the peak to be at 10 degrees 2 theta. For N equals 2, the peak would be at 20. This is a very large D spacing. What I've chosen as an example here, 8.8, is quite a bit larger than you're going to see in really any metal or ceramic. That would be an organic kind of question here. But what this is saying is that I have various depths. So I have this depth right here, which is D times, it's just one of its own. Mm-hmm. But this is 2 times D, this spacing here. And I can go even deeper, that's 3 times D. And each of those is going to have its own reflection. So that's what we call these, is reflections. So I'm going to get, for this 1D spacing, I am going to get a peak at 10, and a smaller peak at 20 and an even smaller peak at 30. So we call these two reflections. Sometimes you don't even see the reflections because they're so much lower in intensity. But especially if you're looking at a single crystal, you're going to see one really strong D-spacing, and then you'll see another little peak way off in the distance.
Okay.
You'll be like, why am I seeing a second peak? It's a single crystal. There should really just be one solid unit cell. And the answer is because it's a reflection.
Cool.
Now let's talk. So that was like, how does N affect things? And it's those reflections. Next, let's talk about how wavelength affects things. So I have one wavelength that is 1.5406 angstroms. And I have a second wavelength, that's a 2, not that you can tell, 1.5444 angstroms. And we can do our very best to try to, filter out those K alpha 2 values. So I'm only getting the 1.5406. But none of our instruments have a really great monochromator, so we deal with this. And monochromators are pretty high tech, so not every XRD is going to have this. So let's say for a D of 2 angstroms, for a D spacing of 2 angstroms, wavelength 1 is going to give me a peak at 45.3061. And that second wavelength, the, black sheep of the family, is going to give us 45.4241. So this is assuming that N stays the same. Move that down a little bit to make it a little better. There's a break in the data here. And you can see we've got a difference of about 118-ish degrees. So remembering that 2 angstroms, that's going to be up here on the right-hand side of our graph. And that's pretty significant. Our step size for XRD is usually going to be 0.02 degrees. So that's our step size. So we're collecting 6 steps in between the first and the second peak of the same origin. So that's significant enough that you can visibly see it's going to look, my goodness, so many emails. It's going to look something like this with 2 very distinct peaks. Okay. One easy way to tell that it is K alpha 1, K alpha 2 is the height of the second peak is usually about 1/2 of the total height of the big peak. And there's a little bit of space here where both of them were kind of happening at the same time. So it doesn't usually drop all the way down. But at much, much higher angles, it will sometimes drop down entirely. But they'll just be right next to each other. They will have this predictable offset. And you're like, yeah, that's K alpha 2 for sure.
Sure.
So that's on the rightmost side of the graph. On the leftmost side of the graph, so let's talk about D equals 4 angstroms. That's still not leftmost side of the graph, but it's farther to the left. I'm going to have my first peak is going to happen at 22.2062 degrees. My second peak is going to be 22.2617 degrees. And if you're feeling like you really want to do the math, you're welcome to do that later. I'm not going to make you do it because the internet can do this math really quickly for us. You're like, hey, I want a Bragg's law calculator. And it's like, here you go, a Bragg's law calculator.
Perfect.
So the offset on this one is 0.055 degrees. And you'll notice that that's a pretty substantial difference between those. It's a much smaller offset. This one is going to look like this. So I've got the same thing where the height of one peak is about half. But this one is going to look more like a shoulder and less like an independent peak. So remembering about our, like, the way the graph is going to look is that this is going to be on the right-hand side. Oops, I should not have done that. That was fun. This is going to be on the right-hand side of the graph, where the shoulder is going to be more present on the left-hand side of the graph. So if you have K alpha 2, you'll notice that the shape of your peaks changes as you go along the x-axis.
Okay.
So those are kind of three ways to tell that you have K alpha 2. One is you've got these little half-height peaks.
Mm-hmm.
2 is that it's right next to another bigger peak. And 3 is that it changes from this to this, from left to right on the graph.
Cool. Makes sense.
Other than being kind of annoying, K alpha 2 doesn't like ruin our data. The real problem is it's not useful to us. We need one predictable wavelength in order to figure out our d-spacing. We don't want to be working with two variables. So there are a lot of softwares that will help you take this peak and sort of like extrapolate what the peak might look like if it didn't have that shoulder. Because that shape of the peak can be really useful to us.
Mm-hmm.
For sort of the analysis stuff that we do afterwards.
Sweet.
Okay, let's talk about stuff that doesn't really work in XRD. So we talked about the purpose of XRD is long range predictable order, right? We are aiming for something that is crystalline. In this application, we're talking about something that's powdered, so it's going to be random orientation.
Mm-hmm.
It could also be like a piece of metal that you quench, or you receive a part and you're like, I want to see what this is. You can throw that in an XRD, as long as you have generally randomized orientation. You don't want everything to be facing one direction. But even in that, let me see if I still have it pasted. That was fun. I don't still have it pasted, bummer. So even in this orientation, which one are we gonna grab? We're gonna grab this one. So even in this orientation right here, we have the x-rays are bouncing off of my kind of blue lines here. But the x-rays that come in, I'll draw them. How am I going to draw them? I want a stroke eraser, that's good. I'm going to erase the blue here to make it a little bit less noisy. But let's say I've got my x-rays that come in here, this direction. Mm-hmm. They're gonna diffract this way.
Right.
Because I've got this angle in, this angle out, right? There's no detector over here. So I'm not going to get any information about these planes. I'm gonna silence that phone. I probably should have silenced that phone a while ago, but here we are. So we are actually mostly looking at horizontal planes as well. So in addition to long range, predictable, homogeneous, randomized order, we also were just looking at these flat planes. So what happens is with this particle of salt, I'm going to be collecting data about these ones. I will not be collecting any information about these kind of sideways. But I am going to assume that I have a rotation capability on here. I'm gonna assume wrong. How do I not have a rotation? Like can you? It's annoying. It's fine. We're gonna just redraw it. So now let's say I've got and then nope. So if I were to turn this around, now I've got my blue lines are like this. So I've tilted it upwards. But those purple lines from earlier are now horizontal.
Okay.
So this is particle 1 here. And it's doing a great job of showing my detector this blue despacing. But if I don't have particle 2, then I'm never going to see any information about the purple spacing.
Right.
So by having 2 salt particles, 2 little crumbs of salt instead of just the one, I'm now getting additional information.
Okay.
So this is where we want randomized orientation, is because the different ways that I rotate this, a full 180, or I just rotate it 45 degrees, or maybe I flip it forward and now I'm getting, what I can't see in this 2-dimensional plane here. Each particle is going to diffract from a different plane, and so I'm going to get the full view. Salt has this fun thing where even its tiniest little particles are cubes. And so if I were to just lay them all on a glass slide and I have one thin layer of salt cubes, there is not going to be random orientation. This is just as bad as running a single crystal because I just have one despacing that's going to be represented here. So this would be an oriented powder. That's what I've drawn on top there. Or a single crystal, or an oriented solid. So any of these options where I have perfect alignment. This is my solid sample here. I'm going to just get one little bit of information. And my problem is that I'm going to get probably just like one peak. Plus maybe reflections.
Right.
Maybe. There are plenty of ways to study those materials, but the Bragg-Brentano orientation, which is what we're talking about today, is not suited for these kind of materials.
Okay.
Other than maybe telling us the direction it's oriented. It's like, yeah, this is, face up. And you're like, yeah, great, thanks. But you can't learn a lot about the other dimensions of the material. That would require rotating the material or maybe passing the x-rays through the material instead of bouncing them off. With good orientation, you'll have some in that straight up and down orientation. Wow. I apparently cannot draw on. There we go. I'm trying, man. There we go. To the best of my ability, I've now got randomized particles.
Right.
And usually this is going to be accomplished by putting them on a surface that's kind of bumpy. Because salt, like I said, if I put it on like a very flat, like glass slide or something, it's going to just orient itself. So I put it on some sort of bumpy surface. Or if I've got a solid, it should have grain structure to it rather than, and I'm not going to attempt to draw everything. Probably, I don't know, maybe I'll just draw everything because I'm having a good time here. But the inside of the material, I should have grains facing one way and another, and they should all have been, grown in lots of different directions if I'm going to be getting a really great date on this. Our sample holders, we've got 3 kinds of sample holders. One of them is super deep. And because it's super deep, we get these particles laying on top of each other randomly. It'd be like, really, we're going to silence that. That's getting really annoying. It would be like dumping a bunch of dice into a bucket, where like eventually they're not going to sit flat. The first layer is probably going to sit flat, maybe even the second layer a little bit, but eventually they're going to sit on top of each other and they're going to be all sorts of random directions by the time you get to the top layer. Yeah. So one of our sample holders is deep. One of our sample holders is sandblasted. So as long as you have small enough particles, there's a bumpy surface for you. Okay. And then our last one is actually macroscopically bumpy. You can see the bumps. It would be sort of like if you took your fingernail and pressed it into clay, you can see the like ridges. Right. So all 3 of ours have the ability to create good orientation for these kind of samples. There are samples that are going to be really like hard. Like this is like lots of peaks. And I'll do a smiley face. Yay. So good orientation for this Bragg-Brentano geometry here. That's ideal for the way this XRD is set up. Some samples are just really gonna struggle. So no matter what, anything that is magnetic is gonna have a preferred orientation. It's gonna align itself north to south. Right. There's very little you can do about that. Anything that is needle-like, so that would be like your particles are long and skinny. It can also be platelets, and I'm not talking just like about blood platelets, but anything that is sort of flat. Mica is a really good example of that. It's flat and thin, sort of like a plate. All of those are going to kind of interact with each other. They're going to stick, they're going to align. And things that are highly staticky. So things that are really staticky are also going to, they're going to orient themselves similar to a magnetic sample would. Right. Those you just have to take extra special care, whether that's running it on an XRD that's better with preferred orientation, which, by the way, preferred orientation or induced orientation. Basically any like non-randomized, any directionality in a sample. We call that texturing when we're talking about XRD stuff. So you can actually refine for texturing when you're looking at the data. You're like, actually, I know that my sample was run in such a way where it's probably going to be oriented, and you can sort of, not like back calculate, but you can sort of minimize the effect of the texturing if you know it's happening.
Okay.
But if you see that word, texturing, that's what that is.
Gotcha.
So let's talk about some fun and unique applications for the last little part of this video. And I've said it a bazillion times, but I'm going to say it again. This is unique applications for Bragg-Brentano geometry, or that setup of kind of the goniometer with the source and the detector and the way I've drawn it all out. There are XRDs for which this maybe isn't unique. And it's like, I specifically built this XRD to do this application. There are some XRDs that will be able to do these, some that won't. It's just like, depends on the person. Single crystal XRD is, I think, maybe the next biggest field. But there's also like small angle X-ray scattering and wide angle X-ray scattering and lots of other things that we can do with how X-rays bounce off of crystalline structures. So for the posterity watching this video, I don't want anyone to think like, what a narrow field of view. I really am. That's the goal. Narrow field of view today. All right. So one of our unique applications is amorphous materials. Do you remember what an amorphous material is?
Non-crystalline.
Non-crystalline. So amorphous materials, do they have spaces between their atoms?
Yes.
Yes, of course, because they have more than one atom, so there are spaces between them. And just because they don't have a regular spacing between each of their atoms doesn't mean that there isn't some average. So with amorphous materials, they have no repeat unit, no regular spacing. This is very typically going to be like a polymer or something organic. But I mean, you've probably drawn like an organic molecule where I've got the zigzags here. I do have a bond length. And I could, if I, pulled up the Google, I could say carbon-carbon single bonds and carbon-carbon double bonds and carbon-carbon triple bonds. Each of those has a specific bond length that I could look up on the internet. That I'm like, yeah, most carbons attach to other carbons at a specific distance from one another. So while I don't have a repeat unit, I do have sort of these repeat spacings present in my material. And what I end up with as far as my graph is concerned, and I'm gonna actually put units on this. This is 5 to say like 30. So we're on the kind of small or low 2 theta range. Thinking about it, 5 degrees 2 theta means that my source is at 2.5 above horizon.
Okay.
And my detector is 2.5 above horizon. Like we're
Right.
very, very small here. Basically straight on the material. But that is a very large D-spacing down here, that 5 degrees. And my data is gonna look, ooh, that was terrible. My hand slipped off the desk. That was really embarrassing. The data is gonna look something a little bit like this. So it's not a peak. What we were looking at before, the width of those peaks was maybe half a degree, maybe even like a tenth or smaller of a degree. those were like semi-crystalline is what I was drawing. Is like they're not perfect single crystals,
Yeah.
but they're gonna be pretty small. An amorphous peak is going to be very wide, and you can think about it sort of like statistics. I can do sort of this statistics thing where I've got the average bond length. I can also look at like standard deviation, sort of like the width of the peak. So I can get ideas of maybe, what is are most of my bonds carbon-carbon double bonds or carbon single bonds. Of course, that's only going to work if I have a simple enough material that I have a list of 3 to look at instead of a list of, maybe 10 or 20 or 30. But by having this idea of average bond length, I can also maybe guess about cross-linking, because cross-linking brings molecules closer together. So I would have a smaller D spacing, which smaller would be moved up here. Or maybe if the material is heated, or if it's a hydrogel, maybe if it's expanded because it's taking in water, I'm going to expect a larger D spacing, or in this case not D spacing, a larger average bond length. So I would expect a peak shift. So while this isn't like exactly the science that we do XRD on typically, we can still get meaningful data out of amorphous materials. By way of information, a semi-crystalline material, and that's something that has some amorphous content and some crystalline content. Really common example of this would be soil. We have some rock material, so we probably have some silica, and we probably have some iron oxide and a couple of other crystalline things. But we also have a whole bunch of organics, the worm poop and all the things. So we still are going to have the same like hump, and it's going to be over the same range, but I'm also going to have those crystalline peaks come off of it. So using my eraser here to make it look like an actual XRD scan, it's going to look a little bit like this. It's reacting so very slowly because it's doing 100 things at a time. So we're going to have this sort of like combination. The amorphous hump is what we call that. It's not going to hide the crystalline peaks, nor will the crystalline peaks hide the amorphous hump. It's just literally additive.
Gotcha.
The curvy background can make it a little bit harder to read where exactly a peak starts and stops, but still that can be kind of corrected for. Questions on amorphous materials? Rad. Let's talk about thin films. And this is usually like a film that I would measure on the nanometer scale, because thin can mean different things in a lot of different applications. Thin films are typically going to be deposited on a substrate of some sort. So I've got a substrate that's going to be a couple millimeters thick maybe. And then I've got this maybe like nanometer film laying right on top. It's this very, very thin. Imagining our original setup where I've got X-rays coming in, X-rays coming out. You can see that my X-rays, they are going to penetrate some distance into my sample. We know that that's the case. It has to, right? But I have, in this example, maybe like 1/3 of the X-ray interaction, like the depth of interaction. About 1/3 of that is actually on the film, and another 2/3 is in the substrate. So what that means is at best, the peaks from the film one-third of the height of the substrate. In this situation. The reason I say at best is because most people choose silicon single crystals as their substrate. Silicon single crystals are the equivalent of like a stadium's worth of speakers in terms of how loudly they bounce back X-rays, to the point where you maybe won't even see the film at all.
Wow.
Because silicon single crystal is so diffractive. So that's obviously a problem because I'm probably trying to study the thin film and not the substrate.
Right.
So our solution is we've got our substrate, same thing, big old substrate, tiny little film. And what we do is we actually let the source come in at a really, really low angle. And I am talking like 1 degree 2 theta. Let me see if I can draw that properly. I just drew like 8 lines to get 1 line. We're gonna try. And this is like omega equals somewhere between 1 and 5 degrees. The X-rays are still going to bounce off the sample in all sorts of different directions. And so what I do is I move my detector farther.
Okay.
Because 2 theta is always equal to omega plus theta, I'm still getting an equivalent 2 theta. This is one of those examples where theta is not the same as half of 2 theta.
Gotcha.
Because my omega and my theta are no longer equal to each other. So what's nice about this is because I'm skimming across the surface there, you can see I'm collecting the full length of my X-rays are staying in the film, never interacting with the substrate. The only trick is that the detector has to travel a little farther, and I have to be sensitive enough to pick those up. So there's usually a little bit of extra oomph on a thin film detector. And the goal here is no substrate interaction whatsoever. A little like sub problem with thin films is they tend to be very oriented. There's not much you can do to make a thin film randomly oriented. So that's its own set of problems, but still. I'm gonna scoot that down so it's not on top of its neighbor. So those are thin films. That's pretty much, that's the thought. Any questions on thin films? And actually I should draw this. In normal X-ray diffraction, both the source and the detector are moving.
Yes.
In thin film, this is stationary and the detector is moving.
Okay.
So keep that omega angle just real low.
Yeah.
Okay, now let's talk about nanomaterials. I took a nanomaterials like elective course when I was an undergrad, taught by Dr. Tawari, who teaches some of our other undergraduate classes as well. And this like blew my mind, learning this particular thing, which is why I always include it, because I think it's so interesting. So a nanoparticle there's actually a limit to what we call a nanoparticle, as in 1 atom is not a nanoparticle, 2 atoms is not a nanoparticle. A nanoparticle is 9 atoms or more, which is insane. 9 atoms is absolutely nothing.
Right.
like that is like one unit cell. Right? Like
Yeah.
I've got 1, 2, 3, 4, 5, 6, 7, and then I've got this one in the back, 8. And then let's say I've got like one in the middle as well, right? Like there's not a great way for me to draw the one in the middle. One in the middle.
Yeah.
That's 9 atoms. Ta-da, a nanoparticle.
Huh.
Does this have long range order?
No?
No, it doesn't even have a long to range, right?
Right.
So most nanoparticles have no or very little long range order, which means I probably can't get enough X-rays to bounce off of each plane to get any significant constructive or destructive interference.
Right.
What nanoparticle XRD looks like if I were to take a nanoparticle. It's gonna look like this. And I am working on the scale of like 0 to 9, or sorry, not 0, because we don't ever go down to 0, 0. Maybe that'd be like 10 to 90. I am working on the same scale that I was when I drew this.
Okay.
And the big difference is the width of the peaks. So I'm going to end up with very wide peaks. Do you remember why amorphous material had a wide peak?
No.
It was, and I didn't say it in these words exactly, it's basically due to uncertainty or irregularity in it. So amorphous materials, they have a variety of bond lengths because they're not crystalline. Nanomaterials have a variety of bond lengths because there is no long range order. And so let's say this atom right here, this is my unit cell, right?
Mm-hmm.
That's one of my particles. Paste. Now let's say that this one got just like stretched ever so slightly, where this one got smooshed that way. I now have the same unit cell and all three of them has a slightly different A, B, and C value, meaning any repeatability to them is very minimal.
Okay.
So this distance here is indicative of uncertainty or irregularity in A, B, C, alpha, beta, gamma, etc. I still have, like, I can have a D spacing. I can still get some information. I can get quite a bit of cool information about, like, averages and things. I can treat it sort of like a bell curve in a statistics class. But there is an equation called the Scherer equation. Scherrer. And this is the thing that I think is so cool about nanoparticle XRD, is you can use this to determine nanoparticle size. So the Scherer equation is tau equals, I think that's a kappa, not a k, but I write them the same. So kappa times lambda divided by beta cosine of theta, and remembering that this is 2 theta divided by 2, not theta.
Yes.
Because we're all really good at that. So this is, tau is the particle size. You can also use this for grain size. So if I had, for some reason, accomplished a nano grain material, which would be really impressive
Yeah.
and super cool. K is a shape factor, so assuming that our particles are probably not perfect spheres. But you're welcome to assume whatever the heck you want about your material. Lambda, we've been working with, that's 1.5406 angstroms for our copper source.
Mhm.
There are other sources that are not copper. That lambda I said is, that theta is 2 theta divided by 2. And beta is the broadening. There's a little bit of instrument calibration that you have to do to get that factor. But broadening is this width right here. How wide is the peak compared to how wide would the peak be if it wasn't a nanoparticle? And that's this value here. So like we already have the theta, we already have the lambda. Shape factor is a little bit of complication, but like generally a fairly straightforward equation.
Right.
And boom, we have our particle size. This only works for nanoparticles because when you get to about 10 microns and above, they're going to behave random. They're going to be random orientation,
Right.
nice long range order. This only works on things that don't have long range order. So there's a limit to this. But I think it's so stinking cool. We can do that. All right, we're going to talk about two more kind of weird samples. We'll try to do that before 5 p.m. So the next one we're going to talk about is non-homogeneous surfaces. Let's say I've got a rock, and I'm going to draw a picture of my rock rather than the rock itself. But the rock has these sections where it's like greens and reds and whites. And I throw this in a microscope and I can see where these 3 sections are separate from one another. If I take my XRD scan here, I'm going to say that I probably have 1/3 of A, 1/3 B, and 1/3 C. But if I bump my rock to the left by just a couple millimeters and I'm now collecting data from here, I'm going to say 100% of my material is material A. And I'm going to get no B and no C. So I'm not getting a bulk analysis. The other struggle is that the actual area, the size of this square, changes as 2 theta changes for most XRDs. There is a way to not have that happen. But that means for here, when I'm at low 2 theta, I'm collecting all of this. At high 2 theta, though, I'm actually only going to be collecting this rectangle. So my percentages are going to change with my angle as well as my sample placement. I don't really have like a solid solution here. There are place-specific X-rays that can like tell you X-ray at this position and at this position and at this position. So related sort of to microscopy.
Okay.
Gold standard would be crush up the sample. Basically just like get the sample as homogeneous as possible. There's only so much we can do. The biggest problem that I've seen this with is geologic samples. But this can also be on metals, especially if you have created a metal that has a phase separation. We've got a little bit of like like beta phase and a little bit of the gamma phase.
Right.
If those are not evenly dispersed through the material, if there's more of one phase on the edge where it cooled faster versus the other, it can be really tricky to do XRD and get a true sense of what you're looking at.
Right.
So just don't do non-homogeneous samples.
Yeah.
Last one I want to talk about is ferrous materials. Those are materials that contain nickel, or oh my gosh, iron. I will say nickel in a moment, and it's going to make sense why I said such a stupid thing. And I'm going to say ferrous materials first, iron-rich materials first, because that's the most common element that this happens for.
Okay.
When a copper X-ray hits iron, the iron actually gets excited, and then it relaxes, and it emits an iron X-ray.
Hmm.
Iron does not bounce copper X-rays.
Interesting.
It absorbs and then re-emits. And the problem is it's going to re-emit at every freaking angle. There is no uniformity. There's no diffraction happening anymore, right? Because diffraction was a reliable input angle, output angle
Right.
thing we can figure out. And that iron is just going to spit its own X-rays everywhere. This is also true of cobalt, nickel, and to some degree you'll see it in manganese as well. Manganese and chromium, we'll see it as well. Iron, cobalt, and nickel being the main culprits, and iron being everywhere.
Okay.
What the data looks like here is at lower angles, our background's going to be really high, and our background's going to slope down. So my data on that is going to be like this. My peaks will be normal. I've drawn sort of wide peaks because I was going fast here.
Okay.
But I end up with this background line that isn't flat and is sort of sloping. Just like with the amorphous or the semi-amorphous material, it makes it a little harder to tell where a peak starts and ends.
Right.
Also, I don't want something just emitting X-rays everywhere. That makes my signal just noisy and crappy. The reason this happens is if we were to look at the periodic table, I have copper right here. Right before it is nickel. Right before nickel is cobalt. Right before that is iron. And then the two before that are manganese and chromium. And I'm going to put vanadium on there because that's the number of things that I put. But I've got like a real bad problem with these guys. And sort of a like, I'll do that sort of yellow-green here. Medium bad problem with these guys. Each of these elements, the iron, cobalt, and nickel, and then the chromium and manganese, they are just slightly smaller than copper, which means that the energy that copper puts out is really close to their own energy, which is why they're able to absorb it and then re-emit their own, because their own energy is just slightly smaller than copper's. So they absorb copper and then emit their own slightly smaller wavelengths. I think it's actually a larger wavelength because it's a smaller energy.
Okay. Interesting.
Anyway, they slow down the X-ray as it comes through. The solution for this also is don't. But the solution for this is a non-copper anode. One of our instruments has the ability for the source to kind of discriminate against wavelengths that are not copper. So there's a little bit of sort of a monochromator type situation that we can do to make sure that we're only getting the good copper wavelengths back. But if you're doing a lot of this kind of analysis on iron heavy materials, one of our faculty does actually in a lab directly upstairs from ours, and she has a molybdenum source. So a non-copper anode. She uses molybdenum because a lot of her work is very iron heavy and nickel heavy, and she didn't want to deal with this constantly.